Welcome to the Explainer. Today, we're going to talk about something that's happening all around you right now, but it's completely invisible. It's this hidden world of heat transfer, where every single object in the room with you is in a constant conversation, sending and receiving energy in ways you can't see, but you can definitely feel. So let's kick things off with a question. Have you ever been in a room where the thermostat says it's a perfectly comfortable 22 degrees or 72 Fahrenheit, but you still feel kind of chilly? Why is that? Well, it turns out the air temperature is only one part of the equation. The real answer is in an invisible dialogue happening between your body and the walls around you. That chill you're feeling, that's your own body heat radiating away from you, directly to those colder walls. It's a form of energy exchange called thermal radiation, and it has almost nothing to do with the air. It's all about what surfaces can see each other. And by the end of this, you're going to understand exactly what that means. We're going to break this all down. We'll start with this idea of invisible heat, then dig into its geometry. We'll cover the rules of the game, and then I'll show you this incredible analogy that makes it all just click. We'll even see how to hack heat flow, and we'll finish up with a totally new way to see the world. All right, first up, heat you can't see. You probably know about conduction, right? That's heat through touch. And convection, which is heat moving through air or water. But there's this third really powerful player in the game, radiation. Just picture a campfire. You don't need to actually touch the fire or stand in the hot smoke to feel its warmth. Nope. You can be feet away and still feel that amazing glow on your face. That is thermal radiation. It's energy that travels in perfectly straight lines, just like light, from the fire straight to you. So if this energy travels in straight lines, well then the shape of things, their orientation, how they're positioned, all that stuff must be incredibly important, right? It is. And that brings us to the geometry of heat and a really key idea called the view factor. So what is a view factor? It's actually pretty simple. It's just the fraction of energy leaving one surface that hits another surface directly. But here is the crucial part. It is a purely geometric thing. It has nothing to do with temperature or what the objects are made of. It is all about their shape, their size, and how they are arranged. It's literally about how well two surfaces can see each other. So, for example, a totally flat surface, or one that curves outward, can't see any part of itself. So none of the radiation it sends out can ever come back and hit it. Its view factor to itself is 0. But a concave surface, like the inside of a bowl, it can see itself. Energy leaving one side of the bowl can totally hit the other side. So its view factor to itself is greater than 0. And the same idea applies to how different objects see each other. You have two little plates that are really far apart. Well, they're barely going to see one another. Their view factor is super, super tiny. But now look at this perfect setup. A small sphere completely surrounded by a bigger one. Every single bit of energy leaving that inner sphere has to hit the outer sphere. There's nowhere else for it to go. So the view factor from the inside to the outside, it's exactly 1. Okay, you might be thinking that trying to calculate these view factors for, say, a whole room sounds, well, really hard. And you'd be right. But luckily, engineers have some really smart shortcuts. They don't have to figure out every single one from scratch. They mostly rely on two main rules. First is the summation rule. The idea is simple. All the energy leaving a surface has to go somewhere. So if you add up the view factors to all the things it can see, the total has to be 1. It's simple, but it's really powerful. The second one is the reciprocity rule. This one is just an elegant little equation that connects two view factors. It often lets you find a really difficult one by just calculating an easier one first. And just how powerful are these shortcuts? Get this. If you have a simple box, 6 sides, you'd think you have to figure out 36 different view factors. But by using these two rules, you only have to actually calculate 15 of them. The other 21, they just fall right into place. It's a massive time saver. Okay, we've got the geometry handled. Now for the part that feels like a magic trick, the part that makes calculating the actual amount of heat transfer feel surprisingly simple. We're going to start thinking about heat flow like it's a basic electrical circuit. Now, to build our analogy, we need one more term. It's called radiosity. The best way to think about this is like it's the voltage of a surface. It represents the total energy leaving that surface, and that includes both the energy it's creating itself because it's hot and any energy that's bouncing off of it from somewhere else. So here's how the analogy works. In an electrical circuit, right, a difference in voltage is what pushes a current through a resistor. While in our radiation world, the difference between what a surface wants to emit because of its temperature and the radiosity that's actually leaving it, that difference is what drives the heat flow through something we can call a surface resistance. This lets us build this amazing one-to-one map. The actual flow of heat, that's our current. The properties of the material itself, that creates a surface resistance. And that view factor we talked about, the geometry between objects, that creates a space resistance. All of a sudden, we can take a really complex heat problem and just draw it as a simple circuit. So what's this actually good for? Well, let's use our new circuit analogy to do some real-world engineering. Let's figure out how to stop heat from getting from point A to point B. It's time to hack the flow. Okay, imagine two plates sending heat back and forth. The circuit is simple. You have a surface resistor for plate 1, a space resistor for the gap between them, and another surface resistor for plate 2. Now, let's just slide a thin shield right in the middle. Well, that shield is just another surface, so we've added its own resistance, and we've created a whole new space for the heat to cross. We basically just put a bunch of new resistors into our circuit. And what happens when you add more resistance to an electrical circuit? The current slows down. It is exactly the same for heat. It turns out that adding just one single thin shield can slash the amount of heat transfer by a whopping 77%. That is the power of thinking with this analogy. And this whole radiation effect isn't just for big industrial machines. It's happening everywhere. It's the reason why a thermometer you put in a sunny spot will read higher than the actual air temperature. That little sensor isn't just measuring the air. It's also seeing the hot window and the sunlit walls, and it's soaking up their heat too. Okay, let's bring it all home. We've gone from a chilly room to campfires to electrical circuits. Now we can finally put all the pieces together and see why this matters. So, what are the big takeaways? First, the view factor is how geometry controls the flow of heat. Second, thinking about radiation like an electrical circuit is a game changer for making hard problems easy. These aren't just abstract ideas. They're used to design everything from furnaces to spacecraft. And of course, it's why you can feel cold even when the thermostat says you should be comfortable. So, I'll leave you with this final thought. Just look around the room you're in right now. The walls, the ceiling, the window, they aren't just sitting there. They're all in a constant, invisible dance of energy. They're all seeing each other, and they're seeing you, exchanging heat every single second. So, how does knowing that change the way you see the room you're in? Thanks for joining us on The Explainer.